Hi, excited to be here. Second time at Container Camp, actually. And I don't need to reintroduce myself. That's pretty great. So, exactly, I'm going to lower the bar, let me put it like this. We're going to go way down the stack. And I'm going to talk about file system mounts in user namespaces. So, who knows what user namespaces are? Well, a few, okay. I'm not going to bore you with this then. That's good. Exactly. I'm going to use a couple of abbreviations in this talk, so don't get confused. NS is namespace, URNS is user namespace, and FS is file system. It's pretty obvious, but just so that you know. Okay. So I think it's pretty fair to assume that most of you will heard about namespaces at this point, or Linux namespaces. And the reason is usually pretty simple. It's an essential building block of Linux containers. And this is why we're here, essentially. In essence, a namespace is nothing. I'm not going to go do a deep dive here, but in essence, a namespace is nothing but a mechanism, basically, to virtualize an aspect of a system. And the definition implies that there is not just one namespace, but there are multiple. And the namespaces that we currently have are 6 mount namespaces, PID namespaces, UTS, IPC, cgroup, network, and user. And I'm not going to explain all of them because I think I can assume that most of you will know what they do. There are a bunch of in the works, time namespaces, device namespaces, and IMA namespaces, not necessarily in the same way that we currently do namespaces. There's a patch set for time namespaces by the Virtuoso guys who have done a great deal of work around containers. That might be something that will come up later this year. We're going to have a discussion. So basically that you can set a different time inside of a container than you can do on the host, which currently you cannot do, which is something that you might want. A device namespace, this is something I've been working on for a while. This has gotten merged. It's a user space-based namespace, essentially. I'm going to give a talk later this year about this. And there is going to be probably at some point an IMA namespace, so an integrity measurement namespace. But yeah, we'll see. So as an example, for what a namespace does, we can look at the mount namespace, which is usually the one that is the most obvious. They allow for per namespace mount tables. So what this means, if you create a new mount namespace, and it's not, let's leave mount propagation out of the picture for now, so you don't mark the mount point as shared, you can do mounts and umounts in this new namespace, and it will not affect your host or your initial mount namespace, which is a pretty good thing to have. Otherwise, you would always unmount, I don't know, sys and proc if you're in a new namespace. So you don't affect your ancestor mount namespace, which is technically a little incorrect because mount namespaces are not hierarchical, but glossing over that for now. The second one is PID namespaces, which basically allow for per namespace process identifiers, which means every new PID namespace that you create, you start at PID 1, and they are actually namespaces that are properly hierarchical. That means every ancestor namespace can see all of the PIDs in the child namespace. Pretty interesting. There are other namespaces, UTS namespaces per host name, per namespace host name settings, IPC namespaces, which allow for isolated IPC mechanisms, so inter-process communication in cgroup and network. I'm not going to go into all of them. So what are they actually used for? That's for something I said before. They are mainly used for building containers and isolating workloads. So depending on which of those namespaces you actually choose is pretty important, since it determines how isolated your workload is going to be from your host or from the initial namespaces. But what makes namespaces different from traditional virtualization methods is that they are a very thin abstraction layer that is tightly integrated into the Linux kernel. Or into a bunch of subsystems even of the Linux kernel. So the consequence is that namespaces are also tightly integrated with permission checks into the kernel, which means there is no real privilege separation for most namespaces. So for example, just because you create a new mount namespace or a new network namespace, you will still carry the same privileges. It means you can still power off the host, you can still chown files, you can basically do anything that you want, which is one of the reasons why you cannot create any kind of namespaces apart from the user namespace without being root on the host. But since you're using namespaces to run untrusted workloads, you very much want privilege separation. So there's an idea, or here there was an idea a while back, 2013 now, so 5 years. The idea that comes to mind pretty naturally when you already have these prior concept of a namespace is to implement a namespace whose sole purpose is to basically isolate privilege on a standard, or the privilege concept on a standard Linux system. And the base requirements are, if you think about them, coming up with them is probably difficult, but thinking about them, it's actually quite clear. What you want to do is you want to separate the host IDs from the user namespace IDs in multiple ways. The most critical way is, do you want to isolate the privilege that is carried by host IDs from the privilege that is carried by user namespace IDs? What this means is you shouldn't be able to perform operations that affect the host based on the privilege that user namespace IDs carry. You also want to have a user as root ID that is privileged over the user namespace. That means you want to have the same privilege model that you have in the initial user namespace, in a non-initial user namespace. And that is the syntax and semantics of UIDs and GIDs should be preserved in a non-initial user namespace. So for example, you want to carry over the concept of a root ID, so there should be a UID 0 inside a user namespace. And this way you can have the same structurally identical permission models, basically. But at the same time, you don't want this to be a hard requirement. There are workloads or use cases where you, for example, want to have even more privilege separation by not having a root UID 0 inside of the container. This is basically what we would call, well, rootless container is kind of difficult in the sense that it usually means that you map your own UID to UID 0 inside of the containers, by which you now have a privileged UID over the user namespace. What I mean by that is you can, for example, just map UID 100,000 to UID 1,000 on the host, to UID 1,000 inside of the user namespace, and then you don't have a mapping for user and SID 0. And now you have broken the permission model, basically, that you have in the initial user namespace. So there is no UID that can perform all of the privileged operations inside of the new user namespace, which is pretty good if you have hard requirements for security. You want nesting to be possible. This is pretty important, which means you want to be able to create user namespaces inside of user namespaces so that you can have layers of isolation. You need to ensure that the user namespace root ID is not privileged over any resource that it does not own. So it means you shouldn't be able to, for example, mess with any global limits that affect the whole system. That should only be possible for root in the initial user namespace. And you want unprivileged users to be able to safely create new user namespaces as well. So UID 1000 or 1001 on the host should be possible, should be allowed to create a new user namespace. That is again a requirement for fully unprivileged containers. Yup. The way this is essentially done from a kernel's perspective is that you establish a bijective mapping such that you choose a set of user and SIDs and a set of unprivileged host IDs of equal size, and then you basically define a function such that each user and user ID is uniquely mapped to exactly one host ID. That there is no requirement to do this. So again, it means you can choose arbitrary subsets of user and SIDs. However, if you want to retain the full permission model that you have on the host, then you need to basically establish an isomorphism, which the way this is usually done is you choose user and SID 0 up to user and SID 65,536, and then map it to a range of identical size on the host. So a concrete example would be, let's say user and ID 0 to user and ID 100,000 inside of the container will be mapped to basically ID 100,000 to up to 200,000 on the host, which means if you run a process inside of the user namespace now that runs with UID 0, and you look at this output from the host, you will see UID 100,000. So you see that there is no privilege associated with this on the host, but there is privilege associated within that user namespace. Okay, so I can show you, I can give a little demo if that works actually, but it should. Yes. So, what do I mean by this mapping thing I'm keep talking about? Well, essentially this. I'm going to establish a mapping that basically states I want to map both UIDs and GIDs, and then I say from 0 to, let's say I'm making it for 1004, and then I write an arbitrary program in there. So I'm doing it as root now, and then I look at sorry. So what you see right there is you have the first identifier is the user namespace UID. That means it starts off at UID 0 inside of the user namespace. It is mapped to UID 1000 on the host, and the range is 4. So it means 0 is mapped to 1000, 1 is mapped to 1001, 2 is mapped to 1002, and 3 is mapped to 1003. That's basically what this means to establish a mapping. Let me switch back. Okay. So, okay, with few remaining things you need to do is basically you need to, all remaining privilege concepts that you have need to be targeted against a specific user namespace. So you need to introduce the concept, but you should introduce the concept of a owning user namespace. So the things that come to mind are, for example, capabilities. So it means capabilities should be per user namespace so that they can be charged per user namespace. So if you create a new user namespace, you will usually have a full capability set like root UID 0 would on the host, and the kernel can now perform any permission checks against your user namespace. So if you check for a capability, there is a check in the kernel that is NS capable, which means do you have that capability in the current user namespace, not the initial user namespace. That is not always true, which can be confusing from a user space perspective. For example, for a long time, certain capabilities will always be checked against the initial user namespace, so you need to have it in the initial user namespace, but sometimes we remove this requirement, which we did recently for cap make not, for example. So if you wanted to create a device node, it was only possible if your root in the initial user namespace had the capability, the cap make not capability in the initial user namespace. We removed this requirement now. You can do it in user namespaces if you have mounted the file system inside of the user namespace. But yeah, you also introduce a concept of owning user namespace for all other namespaces, which means basically if you create a new user namespace and then create successively all of the other namespaces, they will all be owned by the user namespace in which they have been created, which is pretty cool. So now all of the other namespaces have an owning user namespace, so the kernel can always look, can you do this operation? What is your owning user namespace? Your owning user namespace is not the initial namespace. Tough luck, won't work. This is cool because you can, for example, do stuff which most of you probably know is you can create a new network namespace without unsharing a user namespace first, which means it will be owned by the initial user namespace. And then you unshare a new user namespace, which means you can use the network interfaces to some extent from the initial user namespace that are owned by the initial user namespace, but at the same time can create all other mount spaces now if you want, all other namespaces now, and they still have the non-initial user namespace as owning user namespace. So there's a lot of liberty here. And then obviously resources, all resources, open file limits, and so on, they are all per user namespace. Why am I telling you all of this in this detail? Because to understand why file system mounts in user namespaces are actually a pretty big deal or a complicated beast, you need to understand how user namespaces work in more detail. So, okay, you have an extra layer of isolation and security, which is definitely what you want to use user namespaces, especially if you run untrusted workloads. But they come with a range of restrictions, obviously. These are just a couple of the restrictions I'm going to mention. There are a lot more that are relevant to file systems. So the first restriction is device files, which is something I mentioned before. So let's say you change into a user namespace and you are now able to create functional device nodes. Can somebody come up with an attack right now? For example, exactly, you can get access to any kind of block device that you want to. Or for example, which is one of my favorite attacks, it's basically make not def mem or def kmem and then write into random kernel memory locations. That's also possible. So device files, not a thing. You need to ensure that you can only, you can not create functional device nodes, essentially. SUID or SUID bits, so setuid bits and file system capabilities are another problem. An illustration why this is a problem, it's easy to give for file system capabilities. So imagine you were able to set file system capabilities in non-initial user namespaces. You as an unprivileged user are allowed to create a new user namespace. So you map your own UID that you have on the host to UID 0 inside of the new user namespace, which is always possible. You switch to that user namespace, you create, what do I know, some random binary and set a file system capability on it or file system capabilities on it. Then you switch back to your own user namespace, to the initial user namespace, and now you execute that file with privilege. That's a pretty bad attack. So file system capabilities, not a thing, or you need namespace capabilities, which we now have. A third problem, and this is more a technical problem from the kernel's perspective, are unmapped IDs. So I said before, you can define subsets of UID mappings, so you don't need to map all UIDs and GIDs. So you could only map your own ID, and any file that is not owned by your own UID and GID will show up as nobody no group, so it will not belong to anyone. But if you access a file, the kernel will update the access time, at least if the file system is mounted with that option, which will trigger a write-back, but the write-back will be done with an invalid UID and GID, so you're corrupting the inode. Bad idea. So the kernel cannot allow, for example, so any file that is currently, if you mount the file system in a user namespace, any inodes, any files that have nobody no group will be considered or treated as read-only from a kernel's perspective. Okay, so how do we enable file system mounts in user namespaces? Well, and actually to make this possible, the whole infrastructure, a lot of the infrastructure inside of the kernel needed to be changed over time. There's a bunch of people that have worked on this, and I'm going to mention them at the end. So what is the VFS? In short, it's basically an abstraction inside the kernel that basically dictates what a file system is. It's basically a struct with a bunch of function pointers, because we don't have interfaces in C. And if you want to be a file system, you better implement them. And that is a sort of unique abstraction. How do you deal with all of this? Well, first of all, you need to know what a superblock is, which is pretty easy. Actually, a superblock inside of the kernel is just a struct that contains information about a file system. Name of the file system, what do I know, mount flags, with what mount options it was mounted, no dev or whatever, and no SUID, all that kind of stuff. So if you mount a file system, you need a way of tracking who mounted a file system. So you add a new member to the file system, to the superblock, and you say as user NS, and this records which user namespace mounted a file system. So now you have a concept of, now you can basically say, okay, this user namespace, this was not the initial user namespace that mounted this file system. Second of all, I talked about device nodes, right? So that you have the problem that you can create arbitrary device nodes if you root inside of a user namespace and you have mounted a file system, because you hold privilege over the file system. So you need to restrict the access to device nodes, the ones that are already there when you mounted a file system and the ones you create, essentially. The way you do this is you set iflag as a member in the superblock that basically holds kernel internal flags. and you set the SBI node flag, which means now any access to device nodes inside of that file system, if it is owned by a non-initial user namespace, will be restricted. The third one is the file system capabilities I talked about before. We wrote a patch set. Serge Helen wrote a patch set, he's also a maintainer of LXD and LXC, who namespaced file system capabilities. So right now, you can set file system capabilities inside of a non-initial user namespace. And have it be done safely. The way this is basically done is when you write it from inside of the user namespace, the kernel records the UID that wrote it. And then as a kernel UID, don't worry about it now, but basically then if you try to execute it from another namespace, the kernel will check, is there a mapping for this root UID, for this UID to userness ID 0? If there is, you can execute it. If there isn't, you cannot execute it. So for example, switching back to the host right now, and I have set a file system capabilities in a non-initial user namespace, I cannot execute it. The kernel will just say, you have no mapping for this UID. I'm not going to let you. So we made this secure too. Okay, so now we have all of this infrastructure in place. That's pretty. So now we can allow mounts in file system mounts in user namespaces, right? Well, that's not the end of the story, unfortunately. No, not really. The VFS, as I said, is an abstraction for all file systems, and it handles a bunch of stuff. Most core permission checks. So it checks if you are able to set file system capabilities. It checks if you're able to mount stuff and so on. That's all fine. But this is different from actually file system robustness. So just because the VFS is at this time is at a point where it can, with reasonable certainty, state that we are robust enough to allow file system mounts in non-initial user namespaces, the individual file systems also need to guarantee that they can deal with a hostile userness root. So what this means is the VFS says you're allowed to mount a new file system in your user namespace. Somebody is handing you a disk device with a corrupted file system image. Does something bad, crashes the kernel. Userness root in a user namespace now mounts basically this disk device. You have no control, you cannot restrict it, barring LSMs. You're in problems. You have problems. Sorry, I was almost cursing. I managed not to. And then you've crashed the kernel. So that's a big problem. So this means is each file system individually that you have in the kernel and you care about, the maintainer basically needs to say, yes, I'm confident that I can deal with corrupt images and I can guarantee sufficient robustness. And this is probably not a thing that most maintainers are willing to do. And if so, it's going to be a long way until this will actually happen. There's one exception. You might have heard this or read about this on LWN if you read this. The Fuse file system. Starting with kernel 4.18, we've made it possible to mount Fuse file systems from non-initial user namespaces. Why is Fuse safe? Well, it's in the name. File system, oh my God. File system in user space, great. File systems in user space. What this means is essentially you can write your own file system and all the code that is used to run this file system will be run in user space, and there's a kernel module, the Fuse module, and a library, libfuse, that will do all of the talking between the kernels. So the attack vector is very small, and maintainers have been very confident that allowing Fuse mounts is actually safe. But this is not a very exciting story for you because it basically means you have to write your own file system. You might want to do this. I don't know. So what about other file systems that you might care about? Usually X4, overlayfs, XFS, and butterfs, to just name a few examples, CFS. The only thing I can talk about that will probably be enabled, it might be that we can enable overlayfs. The maintainer needs to be confident. Ubuntu has carried a patch to enable unprivileged overlayfs for a longer time, and we intend to upstream it. The Fuse patches we have already upstreamed. A colleague of mine at my team did the unprivileged Fuse work, or a part of the unprivileged Fuse work. X4 probably not that I heard anything. XFS, ButterFS probably also not. ShiftFS, which is something that my team has been working on, or is currently working on, is designed in such a way that it will probably be it will be mountable from non-initial user namespaces, which is something you might care very much about. You should read up on it. What are solutions to actually mount file systems in a non-initial user namespaces right now that we come up with? Well, they all involve, or most of them involve privilege, basically. One is a new seccomp patch set that a good friend of mine is working on right now, and that is up for merging, Tycho Anderson, which basically allows you to filter syscalls, which means you have a privileged user space process that runs as root. It intercepts all of the syscalls that the container makes. So, for example, a mount syscall that is made. And then seccomp, this new seccomp way of doing is basically defers the decision whether the syscall succeeds or does not succeed to this privileged user space process. So it sends a notification saying, somebody did a mount request, this container. Here's an ID, you can see from what container it came from, and you copy the arguments out. You look at the arguments and you make a decision, for example, this is safe to do or this is not safe to do. This is one solution that you can opt for in future kernels, at least. There is a new mount API coming up, and the way it is designed, I like it a lot, and it's probably going to be a pretty good new mount API designed by David Howells and obviously also Elviro. And what it allows you to do is you have, I'm just going to mention two syscalls. First syscall fsopen, which opens in UFD, and then you have a second syscall called fsconfig, which allows you to set mount options on this file descriptor. And the idea would be, ideally, we would have an option that basically says, make this FD or this mount point mountable by unprivileged users. Then you send this FD to a container, to a new user namespace, and then they can mount. This is also a solution you could opt for. And the last one, which doesn't require privilege, is LKL Fuse, but this is an out-of-tree kernel module, and its idea is to grant access to any file system that the kernel supports, but it's going to come with overhead, and it's not upstream, so that's going to be a problem, actually. So unfortunately, I don't have the really great news that any file system that you ever wanted to be able to mount in a user namespace is going to be available. That's not the reality. But there is some progress. And I think if ShiftFS, for example, makes it into the kernel and is mountable from non-initial user namespaces, that's basically all you need to care about, especially if you care about running unprivileged, I don't know, Docker containers or LXD containers or any type of container that you want. Last but not least, we always forget to mention the people who do the actual work. Eric Biederman, who maintains the namespace and capability, namespace stack inside of the kernel and does a bunch of other great work. He's come up with, I guess, the generic design for all of this, and worked on this a bunch, wrote a couple of patches. Serge and Seth and Stefan, who are all co-maintainers of LXD and LXC with me, have worked on this as well. Some of us have just done design stuff, some of us have act patches. And yes, so these are the ones that actually make this possible. And that's about it.